You said biggest, smallest, most complex. That's the mantra of the Kavli Prize. And we're going to start with the biggest and on the grandest of scales with Ewine van Dishoeck, winner of the 2018 Kavli Prize in Astrophysics. This is only the second time that the Kavli Prize has been won by a single person. And could I just note, woman, both times. Now, Ewine van Dishoeck is a space chemist at Leiden University in the Netherlands. Her work has been fundamental to the understanding of the evolution of stars, planets, and indeed life itself. She's been a very significant scientific leader, coordinating teams from all around the world to bring projects like the Atacama Large Millimeter Array in Chile to fruition. Water in space, space clouds. Ladies and gentlemen, you are in for a fantastic treat. But before we meet her, let's just have a film.
Could there be life elsewhere in the universe? Well, if you want to answer that question, you first have to understand how and where water is formed and how much there is, because water is one of the key ingredients for life as we know it. And what we have learned over the past decades through our observations, through our models, through our laboratory experiments, is that water is formed already on those tiny little dust grains in those dark clouds, even before the collapse of that cloud, to form a new star like our Sun and then a planetary system. Astrochemistry is the formation, destruction, excitation of molecules in different astronomical environments. But it is actually so much more than that, because we can use molecules also as a probe of physical conditions, as a measure of the temperature and the density. Also, the molecules themselves affect the structure and the evolution of clouds by being the main coolants of the gas. And then, indeed, the whole story about the origin of stars and planets. The space between the stars is not empty, but it's filled with a very, very dilute gas, only about 1 atom per cubic centimeter. That is much more empty than anything we can make on Earth in terms of an ultra-high vacuum. But that makes interstellar space also such a fantastic chemical laboratory, because we can study chemical processes under conditions that are very different from those that we normally encounter here on Earth. For millions of years, these clouds are stable, but then a small part of them can start to collapse under its own weight. That's also what happened with our own Sun. It basically originated from a cloud like this. And they are so dark because they contain tiny little dust particles, a little bit like the sand grains that you have on the beach, but then about 1,000 times smaller. And the dust grains are very important because they absorb and scatter the light, so they protect the molecules inside the clouds, but also because they play a role in making new molecules, especially water and organic molecules. To me, it's one continuing story. We started from the large scales of the clouds, then we collapsed the clouds to form protostars and the protoplanetary disks. Now with ALMA we are able to zoom in into those disks and see actually the regions where likely at this very moment giant planets are forming. My dream for the next decade is to zoom in even further, to go very close to the mother star where the terrestrial planets are likely forming, planets like our own Earth, and to study the chemical composition there. And that will actually be possible with the launch of the James Webb Space Telescope and also the extremely large telescopes that are built on the ground. They have the ability to zoom in onto that inner region.
Ladies and gentlemen, will you please welcome the winner of the 2018 Kavli Prize in Astrophysics, Ewine van Dishoeck. And of course, the first thing I have to say is congratulations.
Thank you so much.
Honor.
It's such an honor, and thanks to the Kavli Foundation and the Norwegian Academy and the Ministry for making this possible. It's truly a fantastic honor.
Now, many of us were taught in school that space was this vast, empty place, and a vacuum that contained nothing. Hydrogen and helium, perhaps, but nothing. And yet, there are molecules in there, so many molecules that they've formed the whole of your career. How did these extra molecules get there?
Well, I mean, that's a very interesting question indeed. In the 1950s and 60s, the chemist Dan told the astronomers, don't even bother starting looking for molecules. You're not going to find them because indeed it's mostly hydrogen, helium, and maybe 1 in 10,000 atoms is a carbon or an oxygen or a nitrogen. So how do they ever find each other? How do they make a bond? Now, fortunately, the astronomers didn't listen to the chemists, and they started tuning their receivers, and they found one molecule after another. And so my own fascination has always been with molecules, and mostly from the chemical side. And I was going to certainly continue in that area. But then the professor had died, and so I couldn't continue in my PhD research in that field. And it was my then boyfriend and her current husband who said, "Oh, maybe the molecules in space are something for you." And that's how it happened. That's how I got into that area.
Now, tell me a bit about the abundance of water, because that's become a particular area of yours, and the part that it plays in clouds.
Yeah, so it's actually not so simple. I mean, you have here hydrogen. Hydrogen was made in the Big Bang. And you have oxygen here. Oxygen was made later, so that was made by nuclear fusion in stars. But bringing these two together in this incredible emptiness in space is not easy, because you somehow need to carry off the binding energy of this molecule when you put them together. And on Earth, that's easy because there's always a third body around. But in space, that cannot happen except through radiation. So you need to bring them together on the surfaces of the dust grains. Is one mechanism that we've studied in detail of basically having one hydrogen atom landing on these tiny dust grains, one oxygen atom. They find each other. They meet and greet, and and then they form water. And so there are certainly regions of where new stars and planets are formed, where the bulk of the oxygen is locked up in water.
Tell me about space clouds.
Yes, so these clouds. So I mean, when you look on a beautiful evening up at the sky, you see the stars, you see the planets. You maybe see one in galaxy, but few people realize that in between those stars is indeed this very dilute gas, and that gas is on average about 1 atom per cubic centimeter, and the denser concentrations is what we call clouds. So, but we're still talking only about maybe 10,000 molecules per cubic centimeter. So still 1 million times more empty than an ultra-high vacuum laboratory on Earth. So when an astronomer talks about the dense clouds, it's really still much more empty than anything we have here on Earth.
But they still show up on those amazing images.
Yeah. That's
look at Hubble and
yeah. So the colorful regions that you see, that is the ionized gas. That's not where you find the molecules, but it's in the dark regions, and that's because of these dust grains, these tiny little sand grains, mostly silicates, carbonaceous material, that absorb and scatter the light, and that make it look dark. At least when you look with the light that we have see with our own eyes. Yeah.
I'm interested in the technique, because it seems such a crazy thing to say that you're detecting molecules that exist at a frequency of a few thousand per cubic centimeter. How do you do that?
Well, fortunately, these clouds are big, so you have lots of molecules. So they are light years across. I mean, astronomers like to use dimensions of light years. So you have, in total, you have a lot of molecules, and every molecule, basically, thanks to the laws of quantum mechanics, has its own fingerprint. So you can think of this like a barcode that you have in the supermarket that you can read off, this is my product. And the same happens with these molecules in space.
This is spectroscopy.
Spectroscopy, indeed. They all radiate at specific frequencies, and you can very precisely identify them. So that's really a wonderful technique that we have.
But spectroscopy is a relatively old technique,
Absolutely.
but you also rely on all sorts of new technologies in order to be able to see these clouds.
So I think the big advance in the last decades has been the opening up of the electromagnetic spectrum. So if you take a molecule like this, it can both rotate in space, then it radiates at millimeter wavelengths. It can vibrate, then you can see it at infrared wavelengths. And it can be electronically excited, and you see it at optical ultraviolet wavelengths. And so the traditional way was in the visible, of course, optical, but it's really the infrared and the millimeter wavelengths parts that have been opened up in the recent decades. And you saw the beautiful images of ALMA, for example. That is a fantastic tool for astrochemistry.
So ALMA is the Atacama,
large millimeter array, yes.
which you saw in the film, and is an astonishing thing of beauty in itself.
Absolutely. To me, it's one of the most beautiful places on Earth to be there.
So you've got these large arrays such as ALMA in Chile?
Chile.
But you also use space telescopes like Hubble, and you talked about James Webb, which is going up soon. But when you say astrochemist, we saw video there of you in a lab. A proper wet lab. So it's a combination of laboratory-based experimentation and distant observation.
Yes. Because of course, once we see these molecules and we see, oh, there's water there may be another molecule like this one, dimethyl ether, any other molecules, then of course the question comes, well, why are they there? How did they get there? How are they formed? And then what can they actually tell us? Because if we understand how they were formed, it can tell us something about the history of that material. It can tell us something about the conditions that they have undergone. And so we learn so much more by doing also the simulations in the laboratory and in the computer, actually, also, in order to put the whole story together.
I mean, that guy looked like he was making a martini, but
Yes.
It was suspiciously like a martini glass.
presumably that is not what you do in your lab most of the time.
Well, no, we make actually alcohol.
There you go, okay.
Definitely, we make alcohol.
Now we find out.
And we make a lot of it. I think there's enough in what is it, Orion Cloud, something like 10 to the 29 bottles of whiskey. So
Distributed across where in space?
yeah, you can tap a beer later.
Yeah, okay.
What fascinates me about astronomy is the time that you have to wait for results, because the light coming back is taking years and years and years, and you're waiting 20 and 30 years for results.
So I think there are two time scales here. So there's indeed the light travel time. So when we are observing the Orion Nebula, that happened already some 1,500 years ago, because that's at that distance. So that is certainly my colleagues in Leiden. They study at the edge of the universe. So that those photons have traveled, 13 billion years before finally ending up on the telescope. The other timescale that we have in astronomy is the timescale it takes to conceive, plan, and then build these large facilities like ALMA. So I got involved in the Herschel Space Observatory, which is the main observatory to study water. I got involved in 1982, and it was finally launched in 2009.
That's an extraordinary time scale.
Yes, so that's so you have to at the same time, train sort of the next generation of astronomers in this field. And
you must feel though that we are in a golden age of discovery in astrophysics.
Oh, absolutely.
Just
yes.
time and time again, every year there is a new mission or a new set of discoveries where our understanding of the local neighborhood and the rest of the universe is utterly transformed. I think one of the things that's most striking is the diversity of the universe is far greater than what I learned at school. What's our sort of accounting for how diverse the universe is in terms of the species present?
Yeah, so I mean, certainly the opening up of the electromagnetic spectrum, and of course now we have not just photons that tell us about the universe, but we have gravitational waves that have been detected that tell us about the universe. We have what is called multi-messengers, so neutrinos or other particles that tell us about the universe. So we're learning so much more about the structure of the universe. And yet, I think, indeed, the diversity, but yet we also realize how little we know about the universe. You know, what I'm studying is just what is called the baryonic matter that just makes up 4% of the universe. You have no clue what the dark matter is or the dark energy that make up the bulk of the universe. So
Well, keep
there's
working.
still a lot of that. It's not my field, but I'm happy with those 4% that we can see. But
And there's the continuing missions that we report on, that people like us report on and we talk about in the press all the time. Things like, you know, Cassini went down just last year, and New Horizons, did the fly past of Pluto and is going to look at Kuiper Belt objects in January, I think it is. And then we can't help but notice that you have something quite exciting there.
Yes, what is that?
This is 67P, so the comet that the Rosetta mission from ESA went to, and for the first time actually landed on a comet. In fact, it landed not just once, but it landed actually 3 times.
Well, it bounced.
Bounced on it. But to me, comets are very important to study because they are sort of the most primitive objects that are left over from the formation of our own solar system. So I study the formation of new planetary systems, but at the same time we can look at what happened in our own planetary system some 4.5 billion years ago. And so these comets are really the building blocks of making new planets. They consist of rock and of ice. You know, very much like these interstellar dust grains.
Water
ice. With water ice, but also methanol ice, alcohol ice, that's also present there. And so having a mission that actually, you know, was able to sniff sort of all the gases that are in there and determine its chemical composition, that was just, was like a candy store for us in order to compare with what we see in these clouds.
Just give us a scale on that. So
in reality it's about 4 kilometers in size. So this is a 1 in 30,000 or something like that.
And where is Philae, the lander?
I think it was supposed to land somewhere over here and then made a few hops. I think it's somewhere over there.
Resting on its side.
Yes.
Forever in the shade.
Right.
Poor Philae.
Yeah, but you see, it's very black. I mean, people think of ice as white, but it's not. It's a lot of organic material there, so they are actually very black and very porous, very light.
Now, Ewine, I must ask the question which will, I suspect, maybe in the audience's mind, which is, do you think we're close to being able to detect the signatures of life on planets outside our own solar system? And how important will that real understanding of chemistry that you bring to this field be?
Yeah, I mean, that's, one of the biggest advances in astronomy, undoubtedly over the last decades, has been the detection of planets around other stars. Of course, speculated for ages, but the final, firm detection and proof came only in 1995. So by now we know some 4,000 planets around other stars than our sun. And it's the obvious next goal is to study the composition of the atmospheres of these planets and see whether there are signatures of life that could indicate that life is there on those in those planets. And that's where a lot of the new missions are aimed at, a little bit JWST, but especially the extremely large telescopes and beyond on the ground. Now, it's not going to be easy because just detecting water is not enough. That is a prerequisite to have it, but it's not enough. Also, just detecting ozone or oxygen is not enough. You need a combination of signatures in order to really prove that there is life there. It's not going to be easy. So I think we'll make steps there in the coming decades, but the final proof may take a little bit longer.
What sort of chemistry are you looking for? Is it even possible to detect life on Earth if we were looking at the Earth?
Yes, that's a good question. That's what people have done. They have looked at Earthshine and looked for the signatures there. So definitely a combination of water, oxygen, methane, of course, reduced and oxidizing. You need some disequilibrium chemistry there is important. Vegetation edge is something that you can see. But then you have to believe that, you know, the vegetation on other planets may have the same color as it has here on Earth. That's not.
And of course, it doesn't tell us anything about the type of life.
Oh yes, indeed. I mean, it could be very simple, you know, single cellular life. That's so. So that is, of course, detecting life is first in its most primitive form. I mean, trying to detect intelligent life at distant planets, that's a whole other story.
I mean, I think when we do, you know, science, astrophysics always captures the imagination, doesn't it, of young people in a way that, you know, the only other thing that is on a similar scale is dinosaurs.
Dinosaurs, yeah.
Dinosaurs
and space.
Black holes.
And people can't get enough of it. They absolutely love it. And that it goes that golden age that people are really wrapped up in this discovery. I mean, the reaction to Philae, for instance.
Yeah, was fantastic. But I think that also, you know, means that we have a sort of a task to bring this excitement to the general public, and especially to the young children, to make them enthusiastic, not just about astronomy. I mean, you can use astronomy as a tool for it, but basically draw them into science. And astronomy is a very nice low threshold entry point into sciences for that. And so that is what we really try to stress, sort of. Also in our training in astronomy.
But also when people talk about, you know, the public are not interested in basic science, astronomy is always puts the light to that, because they are fantastically interested in basic science.
And astrochemistry, I guess, you know, not a phrase that is part of the sort of standard lexicon of talking about space, but the notion that you're looking at the chemistry of the early universe or early solar systems. How do you get from, you talked about the big cloud, the protoplanetary disk. Where are we in understanding how you get from space in a cloud to a planetary system such as the solar system?
Yeah, so I think ALMA has really been the big, you know, the transformational step forward in that area. I mean, it used to be that these rotating disks around young stars, you know, that result from the collapse of the cloud, that they were just big blobs. Now, with ALMA, we can really zoom in and see it. So if you compare it with, say, Google Images, it used to be that your city was a blob, and now you see, you know, the canals, the streets, the houses in it. And the same thing with ALMA. You see all of the structure in these disks. We see likely the locations where new giant planets are forming. We see the chemistry that is happening there. So it's you know, all of a sudden it's such a step forward.
And the relationship between observational studies using telescopes like ALMA or Herschel and the space missions like Cassini that then do things like fly through Saturn's rings and have, you know, revelations about the structure of Pluto, none of which we knew before. What is the community like in the sense of, you know, did the spaceship people talk to the astrochemists who talk to the astrophysicists?
Certainly that does. We do so. I mean, of course, every science these days gets more compartmentalized. So there is always a tendency for, say, people working on galaxies and stars and interstellar clouds to have separate conferences. But that's, I think, why it's so important to also have these worldwide conferences like we just had in Vienna for 2 weeks, where we bring all the astronomers together. And indeed, people who work on Cassini actually talk to the astrochemists and the people who are studying solar system formation. So I think that's the importance, to keep bringing, sort of in a broad sense, also people together.
And what are you hoping might come back from James Webb? I mean, and when does James Webb finally launch? It's much delayed, isn't it?
It's unfortunately it's delayed. I saw actually the telescope and the sun shield with my own eyes in early July.
So it really exists?
It really exists. The telescope is fine, the instruments are fine, the sun shield is fine, they just need to be put together. And so there are good hopes that by early 2021 it will be launched.
But what would you hope to find? What would you really wish to see from that mission?
So I think James Webb, even though it was not at all designed for it, so that's the problem. You designed these missions already 20 years ago, when it was basically designed when exoplanets had not even been discovered yet. So it's definitely going to be fantastic for exoplanetary atmospheres. It's also going to be fantastic for zooming in into these inner regions of the disks where the hottest gases are. You're going to see water, simple organic molecules, really at the locations where we think terrestrial planets will be forming. So it's a little bit like, for the last decades we have gone from cloud to disk. In the coming decades we'll go from disks to planets. That's.
I know. I hate asking these questions, and scientists hate being asked it, but I'm going to ask it anyway. When you've just said that James Webb hopefully will go up 21, when do we start getting data back?
About half a year later.
Oh, that soon?
Yes.
Nice.
Well, it needs to go there, it needs to cool off, the instruments need to be turned out and turned on and tested. But yes, it's about half a year later.
Fantastic. Should we let the audience ask some questions? Can we have the lights up?
So thank you for all the fabulous work you've done. I want to ask you, though, because something very unusual about your career. You started out as a chemistry graduate student, and then because your professor died, you had to switch fields, and then you went into another field, but you brought this completely different perspective of being a chemist, and so you were asking questions that maybe the students in astrophysics would not have thought about asking, simply because of what you had done earlier in your career. So I'd like you to reflect just a little bit about what it was like for you as a female graduate student, changing fields, coming in, asking questions that nobody else was asking.
Well, thank you very much.
Let me just repeat the question. So the question was about your early start and how you brought a whole new I suppose, inquiry to a field that had not had your background before, and how was that as a young female postgrad?
Right, yes, so thanks very much for that question. I certainly never regretted the change that I made because, interstellar space is such a fantastic laboratory. It's so much more exciting than a laboratory on Earth. I'm very glad that I had this background because I think a chemist can learn astronomy, but an astronomer has a great difficulty in learning chemistry. So at least at the molecular level in detail. So I came in it the right way, and I think I was actually very fortunate to. I was basically sent to the expert in this field, which was Professor Delgarno at Harvard University, and in fact. Sitting there in the audience, Kate Kirby was there with Alex Delgardo and working also both on the chemistry side and on the astronomy side. And it was just a fantastic environment to be there and very supportive for both male and female students. And certainly both the male and the female were very much promoted by my supervisor.
And you've been a trailblazer for women ever since, because not only have you trailblazed in that particular sense, but you've also pulled together all these extraordinary projects that are across nations, across different disciplines, and actually that requires an enormous amount of skill.
I think the key to all of this is to make sure that people realize that it is a win-win situation when you work together. ALMA is one example where both East Asia and North America and Europe realized that they all had separate projects, but they were all sort of suboptimal. And they realized that, I think we as astronomers helped them realize that by putting it together, you got a much more powerful array because some of the parameters scale with n squared rather than with n, so number of antennas. And so I think that is the key to bringing together these teams and is realizing that it's a win-win situation for everybody, but that everybody also has their own role and can shine in such a large project.
Let's take another question.
As analytical organic chemist, researcher, before I used infrared technique to measure, to identify the materials. And I get the spectrogram. What difference between the spectrogram you get and what we get in the laboratory? That is the first question. The second question, I used to hear from NASA long time ago, perhaps 10 or 20, that they analyze also searching for the life, the molecules of life in supernova remnant. What difference between your work and this one?
The difference between spectroscopy in different situations. Lab.
Yeah, that is a good question. So basically, thanks to the laws of quantum mechanics, the spectrum of a molecule in space is exactly the same as it here on Earth. The only difference, of course, is that the cloud moves with respect to the Earth. So there is a Doppler shift that we have to take into account. But fortunately, because the entire cloud moves all at the same speed, that's very accurately known. You just have to go to one line of one molecule that you know, and that's usually carbon monoxide, and you get the Doppler shift very accurately, and then you can just shift the entire spectrum to your laboratory spectrum.
And the second part of the question was about looking in supernova for these.
Yeah. So supernovas are, of course, very powerful explosions. They are important for chemistry because some of the most complex elements are made in supernova remnants, elements that's beyond iron that you normally don't make in massive stars. So they provide new ingredients that then go into the interstellar medium and that become part of the next cycle of stars and planets that are being formed. But I certainly would not start looking for life in a supernova explosion.
I think we've got another question from there on the fifth row back.
Thank you very much for a wonderful discussion. We're looking at electromagnetic radiation from all over the universe. We're looking at particles that come to Earth. We're looking at gravity waves. We're sending robots to other planets. Is there a tool that you can envision that we're not building yet, maybe because we can't afford it or we don't have enough international cooperation, but is there a tool that you would like to see in coming decades?
I think that question was really, is there a Swiss Army knife
Yeah.
in terms of exploration that we haven't thought of yet? If there was if you had an ideal, what would the different components be? It would need to, besides the horses, getting the stones out of the horses' hooves. Yes.
So I think there are a few answers to your question. First one is sample return. So basically, not just landing on that comet, but also scooping up a little bit.
And that's happening right now with Hayabusa.
Exactly. I was going to say Hayabusa 2 is right at the moment at their target, and that's going to scoop up. That's still not an icy object, so it's a little bit more processed, as we called it. So it's not as primitive as a comet would be, but ideally you would like to have a sample return so that you can bring it back to the laboratory.
So sample return, what else?
What else? ALMA in space. that would be nice.
It's
not going to happen,
yes.
But in principle, of course, getting rid of the perturbing of the atmosphere. So that would be very powerful. I'd like also more of these missions to other comets, like the Rosetta mission. Not necessarily landing and scooping up material, but just sniffing the different parts of our outer solar system, because probably our outer solar system was very chaotic in the beginning. Our whole inner plus outer solar system, very chaotic. And so I'd like to see sort of to what extent that mixing was happening in the solar.
So it's a space telescope that can send back samples and does a lot of sniffing. Anything else?
No, I think.
Do you have a view on so all of the missions that we've been talking about so far have been remote or robotic?
Yeah.
Do you have a view on the future of human space exploration with relevance to your work, doing chemistry on planets?
Yeah, I think the space exploration is going to be rather limited, will always be rather limited for that. I mean, I think the space missions were, of course, wonderful for refurbishing the Hubble Space Telescope. I mean, without that, Hubble would not have had such a fantastic lifetime with new instruments every, 5 years or so. So there, human exploration becomes important, but in general, the kind of research that we are doing, either remote sensing or robotic exploration, would be good.
Okay. We've had another question there.
I'm fascinated by your ability to see what are perhaps oceans of water out in the universe, but diffusely, distributed on these dust grains, and somehow they have to get concentrated onto these comets before they have a chance to impact planets and make real oceans like we have here on Earth. But is there any possibility of using some kind of statistics based on the distribution of water on dust to predict, out of all these exoplanets we're seeing out there, to put a number on how many of those exoplanets might actually have water based on the distribution of the dust?
So this, I think, is a question that relates to what we were talking about earlier about the diversity of how we perceive solar systems now. What sort of techniques will you be able to use in order to predict the constituent elements of planets and exoplanets?
Yeah, so thank you very much for that question. Very good question. Then that brings actually up a point that I should have probably mentioned earlier. So what we see is actually that around every forming solar system, we see lots of water. So there's plenty of water available. There's also plenty of material to form at least one sort of Earth-like planet around these forming solar systems. So the ingredients are there, and they're made already at a very early stage. So I always like to say that the water that you see here in this glass, and I'm going to take a little sip of it, that water is actually 4.5 billion years old. The bonds there were made already 4.5 billion years ago. Now, the question as to what got in the planet, that relates also to snow lines. So where you are in the disk, of course, if it's cold, the water is at ice. If it is warm, it will start to vaporize. And so depending how the planet is built, whether it's built really from these kinds of icy planetesimals, or whether it accretes sort of its gas, its atmosphere as a gas, and whether it does that outside or inside the snow line, that determines then also the amount of water that is present in the atmosphere.
Okay, I think we've got time for one last question, possibly two. There's the mics up there.
I was wondering about your idea about the astroscientists like Stephen Hawking and Carl Sagan and Mike Tyson, and their ideas about multiverse and all those stuff. They have the string theory and the big crunch in the time travel and the future and the latest, updated research just a little bit. I'm not a specialist, but just wondering. Okay.
So I think Stephen Hawking and Carl Sagan, they were fantastic science communicators. They basically started, I was inspired by Carl Sagan's Cosmos. That was just a fantastic show at that time that sort of opened up, I think, science communication at that time. Yeah.
Same for me.
I'm not sure if that was the direction you were going, but I think they were very important for communicating science to the broader public.
And can I ask something? When you were a child, did you want to be an astronaut?
No, I don't think I wanted to be that. But I did have a fascination with just, what is our place in space? Where do we come from? That was certainly a question that has been with me for a very long time.
And the thing you said earlier about a win-win in having diverse labs, of course, the answer to the question, are we alone in the universe? It's a win-win answer.
Yep.
If we're alone, that's amazing. And if we're not, That's amazing.
Yes. Absolutely. Absolutely.
I think we have one more down here in the middle.
So I just wanted to return to the question of signals for life on other planets. And I know that there may be very complex signatures that we have to rely on for that, but is there some kind of astrochemical, biochemical smoking gun that would be one observation that would clinch that, even if it's not the one we're the most likely to see? Is there one thing one might hope for?
So
That's a really interesting question. Is basically there a smoking gun in terms of molecular signatures as to life on Earth? I mean, what would that smoking gun be for you?
Well, I mean, that's a good question, because for a long time people thought there were several smoking guns, and people have now become a little bit more careful about that, because they realize that, well, those smoking guns could be slightly different on other planets. So I think it's now more in terms of likelihoods that it could be life there. I wish there was such a clear signal, but I'm not sure that we know that at this very moment. I think it will really be a combination of signals.
And the models that we look at now, when you look for things like carbon dioxide and methane and oxygen and evidence of metabolism in atmospheres, I spoke to a researcher recently who suggested the best smoking gun might be pollution. The tragedy of looking at a polluted
Then you're thinking already about intelligent or not so intelligent life. I'm not sure that those single-cellular organisms know how to do that.
We've nearly come to the end of our time with you, Ewine, but I wanted you to just look back at your career, which has been crowned with achievements in many different areas. And what has given you the most personal pleasure and satisfaction over that career?
Well, I think the most satisfaction has definitely come from working with all of those young, talented and creative people that I had the pleasure to work with. I mean, it's just been fantastic. A whole series, every few years, of course, in a university, you have a new set of people coming in, but they have all been fantastic to work with. And so when I'm sitting here, I'm really sitting here on behalf of all of them, because they did so much of the creative work.
Well, thank you for inspiring them, for inspiring us, and indeed our audience here today. And if you're watching online, no doubt you've been inspired too. So thank you for joining us. And thank you, Ewine.
Thank you.